All right, welcome. This is the first of what I believe are going to be 12 lectures. We'll have 2 lectures per week. That's the tentative plan. I'll give you more details later on, but for right now, I just want to focus on material in this lecture and communicate with you other details through Canvas. So let's go ahead and get started. What we were working on was Chapter 5. We were working on angular momentum flow and control volumes. And I'm going to start out by reviewing that and then work towards a classic example that puts it all together. So first things first, a bit of review. What we did last time was we took a look at control volumes and we had a fluid flowing in and a fluid flowing out. And we established some sort of pivot or some sort of axis where the device through which the fluid flows could turn. So if this blue represents maybe some sort of piping or something like that, it could pivot this way or it could pivot that way. And in briefly, our theorem is that the change in angular momentum flow of our fluid is going to be the net torque on the control volume. So in this case, we said the angular momentum flow in here is 0, and the angular momentum flow out there is counterclockwise. So we're having a net torque on the fluid in the control volume that way. Okay, and so then by Newton's third law, if there's a force on the fluid this way, there's going to be a force on the pipe the other way. And so we can get what that torque is by doing this calculation. Just a reminder on how we calculate angular momentum flow at any point. So here or here, we're going to take the mass flow rate, we're going to take the distance from the pivot, and we're going to get the speed of the fluid perpendicular to the lever arm and relative to the control volume. And that's a really important idea, that second one that I'll go on later on. Okay, so that's a quick review. Let me go ahead and get an example on the whiteboard and we'll ask you guys to pause or try to work through it as best you can. I think just like in class, I think it makes a huge difference if you take the time to work through it. So classic example, I'll get it up on the board in a minute, but bear with me for lack of a better model, sort of a classic rotating sprinkler. So this is, I took some PVC in the garage and tried to put together an example of a sprinkler. I'll back up a little more. Hopefully you can still see me and hear me. So the idea would be in a case like this is that you would hook this T up to a water source. And this T would be arranged so that the water would flow in. Not only that, but it could also rotate. So it could rotate around either direction. And it's pretty clever if you take a look at rotating sprinkler systems, small or large, how they actually work. Okay, so the water is going to go up and it's going to split with half going one way and half going the other way. And that's not going to cause any rotation. But if you look at it from the side, okay, say look at this point right here like this, the water's going to be moving here like this, and then it's going to be forced to come out this way here like this. And so there's going to be a force of the pipe on the water up. And conversely, there has to be a force of the water on the pipe down. On the other side, there's going to be a force of the pipe on the water down, so conversely there's got to be a force of the water on the pipe up. And so as a consequence, what you're going to end up getting is rotation like that. So a pretty clever arrangement. Water comes out, it splits and goes either way, and you're going to start to get rotation. So what kind of rotation are you going to get? How do you work that out? Well, that's your classic basic equations with torque and angular acceleration that you guys have done in physics. And to get going on that, let me get an example on the board really quickly. So bear with me for just a second. So I'm drawing a sprinkler, trying to get a little bit of three-dimensionality to it. That's not necessary. By the way, if you want to turn to a much better drawing that I have, you can look at figure 5.4 in the book. Figure 5.4 in the book does that. So I got my sprinkler here, and I'll put some numbers on it and get the drawing going. So I tried to get a little bit of an isometric here. The water's going to come in the base. It's going to split with some going this way, coming out like that, and the other going that way and coming out like that. So trying to get a little bit of three-dimensionality on that. Okay, and we're going to make the numbers really basic to start with. And hang on for just a minute. So let let me explain it and I'll have you guys go ahead and get to work and start thinking about it. So the first thing you want to do is, try to maybe do a little bit of a better job with your drawing or visualize what's going on. This is the vertical pipe that comes up, and I'm trying to do an isometric where the water comes up and splits, and some goes to the left and some goes to the right. Okay, and these are supposed to be 90-degree elbows where the water actually turns and comes out here like this and turns and comes out there like that. Okay, so what we're going to try to do in that case is get the torque of the sprinkler on the water. Okay, so what kind of torque is there on that water? And so basically what you're going to do is, remember what we did was we thought about there being a control volume. So your control volume could be the red, and you're going to try to do this calculation, m dot r v theta, in 3 different cases, in 3 different places. So you got this entry, you've got this exit over here, and you've got that exit over there. So what I encourage you to do is just pause the video for a second and see if you can start working out each of these m dot r v thetas. And I'm going to come back and I'm going to work on one of them. You make some progress on it, and then you might want to come back and take a look at my work. Okay. Okay, so I've done the entry. And if you haven't thought about it, maybe pause really quickly and try to do the entry yourself. But explaining a little bit, at this entry here, I've got a mass flow rate of 1 slug per second in here. Okay, and then how far is that from the pivot if I'm going to do my radius? Okay, so if I look at this like here, and I draw this vertical line about which the sprinkler is going to rotate, I have this as a distance of 0 from the pivot. And so basically what we have is we have 0 angular momentum in. This m dot rv is going to be 0. So m dot rv at the entry is 0. Okay, and then what we now need to do is focus either on this side or this side. Hopefully you can see by symmetry they're going to be the same. So if you get one or the other, that's going to be just fine. So I'm going to attack this side over here, try to see what's going on. M dot, that should be pretty obvious. This 1 slug per second is going to split. Okay, R, that's pretty obvious too. It's going to be 1 foot from the pivot. But how about V? So I'm going to take a little work and work out what the speed of this water exiting through the control volume, the speed here or the speed is here. And I want you to do the same yourself and see if your numbers match mine. So to get speed, if you know what you're doing, go ahead and keep going. Okay, but to get speed, okay, we can use this basic relationship. I'll get it up on the board really quickly. Okay, so one of our basic equations for speed entering or exiting a control volume is that relates it to mass dot. Mass dot, the mass flow rate coming out, is the density of the fluid times the speed of the fluid times the cross-sectional area. Okay, we got m dot. It's going to be 1/2 slug per second. Density we can look up in the tables. Speed is what we're trying to figure out. And cross-sectional area, well, this is a 1 1/4 inch diameter pipe, so we'll work it out like that. So I'm just going to go ahead and do the numbers, and you do it yourself. Good practice to see how that works out. Again, you're going to assume the water is that basic density that you get from the basic tables we've been using, 1.94 slug per foot cubed. Okay, if you know what you're doing, keep going, or if you want to pause and take a look at the screen here and see if your numbers match mine. Okay, I solved this equation for V, so I get V as m dot over density times cross-sectional area. The mass flow rate is 0.5 slugs per second. The density is 1.94 slug per foot cubed. And I want to make this area of this outlet right here, this 1 1/4 inch diameter, into feet. So I did 1.25 over 12. And then the cross-sectional area of a circle is pi d squared over 4. And if you go through the units, you should see that all works out. The slugs go away. Okay, the foot cubed and the foot squared end up canceling out to give a foot in the denominator of the denominator, and that'll flip up to the top. So you're going to end up getting feet per second. So let's crank through it a couple times and make sure that we got the same answers. I'm going to work out that speed. 0.5 divided by 1.94 divided by pi divided by 1.25 divided by 12. Then I can multiply it by 4. Okay. And I am getting 30.2 feet per second. I'm going to check that really quickly. Write that down tentatively. 30.2 feet per second. So checking it once again. 0.5 divided by 1.94 divided by pi divided by 1.25 divided by 12, all squared, and then multiplying it by 4. Yeah, 30.2 feet per second. So there's my calculation. That water is coming out at 32.2 feet per second, and that's actually really fast if you think about it. In a second, it's going 30 feet. That water's flying. So we should get a pretty significant torque. This piping needs to turn it from going 30 feet per second that way to 30 feet per second coming off. Okay, so how do we get the torque? Well, once again, we're going to take at this point right here, we're going to take the mass flow rate, R, and the distance and the speed, perpendicular speed to the lever arm. And even though my drawing is not great, this is supposed to represent a 90-degree elbow. So the water's making a 90-degree turn and coming out like that. So let's go ahead and do that calculation and see how the torque turns out. So okay, so I was a little bit lazy with my work. I just went ahead and did m dot times r times v, and I got 15.1. Okay, we should think about how the units work out. This is slugs per second, this is feet, and this is feet per second. And if you work it out, you're going to see a pound in there and a foot left over. So that's foot pound. Okay, so let's take a look at how that 15.1, knowing that it's foot pound, how it relates to the answer. And the book does a very nice job of this, so I encourage you to look at the 15.4, but I'm going to go ahead and do my own drawing of an overhead view, basically, of the sprinkler to see what's going on. So bear with me for just a second. I got that 15.1 up there. So, overhead view of the sprinkler. Okay, so there was this water that came in that had 0 angular momentum, and then there's water that comes out over here that has an angular momentum of 15.1. So I'll put that 15.1 over there. Okay, and then over the same side, the numbers are all the same. It's the same mass flow rate, it's the same distance, it's the same speed, so it's also 15.1. So if we were to put information on there, this is turned 15.1. And that is counterclockwise. And this water here, too, is also turned up 15.1 counterclockwise. So the torque of the sprinkler on the water would be the combination of those two. So if our goal for A is to get the torque of the sprinkler on the water, I'll write it down. Okay, so there would be, if I did my numbers correctly, there would be a nice clear answer. There's basically 30 foot-pounds of torque counterclockwise on the water. This is the torque of the sprinkler on the water. Okay, well the book, and obviously anyone who is doing this sort of a design of a sprinkler would say, okay, well what's the result of that? That's what I have up here for part B. What is the result of that torque? Okay, so that really comes in part from Newton's third law. If if there's a torque of the sprinkler on the water of a certain amount, there also would be the same torque of the water on the sprinkler. So I'm going to write that down. Okay, so the result, symbolically, I could say, look, there's a torque of the water on the sprinkler clockwise, and so in this case, the sprinkler itself is going to start to turn clockwise. Well, how fast? Well, basically, that's that idea. If there's an unbalanced force, there's going to be an acceleration. So the angular acceleration would be the torque divided by the moment of inertia. And certainly that's a problem that we could do. We could figure out what the angular acceleration is. But good enough for now, we know that there's going to be a torque of the water on the sprinkler. The book likes to ask, hey, how hard would you have to hold on to this to actually keep it from spinning? And there would be the answer. You'd have to exert a compensating torque of 13.2 foot-pound. All right, good enough. So that's kind of the start of the classic sprinkler problem. But there's more to it. That would just be at startup. So you got to imagine that you got your sprinkler, and then backing up a little bit. And the situation we were doing was with the sprinkler, what if we just turned on the water? So once the water flows up and gets to that speed, then there's going to be a torque and it's going to start rotating, okay? It's going to start having angular acceleration. But what is the result of that going to be? And interestingly enough, you can actually, pardon me for just a second, you can actually work that out, what the result is going to be, and you'll see that in the problems that I'm going to ask you to look in the book. For homework number 6, which hopefully you're going to be wrapping up very, very soon, Chapter 5, problem 84, is about the arm that's inside a dishwasher. And that's the same thing, that arm in the dishwasher that spins about. There's no motor on that causing to spin. There's plain old water going up and going out the arm and then exiting through holes, and that exit causes it to spin. So a lot of times we use fluids to create rotational motion and can get things going. All right, but then in order to understand what happens once it gets going, what's the angular acceleration and how does that all work out, we need to go back to section 5.1.3 and do some relative velocity stuff. So 5.13.3, let me just get the title up there and talk about it really briefly. Okay, so section 5.1.3 is on moving non-deforming control volumes. So 5.1 is the section where we do continuity, and continuity is the idea that at steady state mass flow in equals mass flow out. Well, that can be true with stationary control volumes, like if you have a pipe just sitting there, but it also can be true with moving control volumes. And moving control volumes, there are some that actually deform. Pretty interesting. Take a look at that in chapter 5. We're going to do non-deforming control volumes. So let me just start with a really, really simple example, and then we'll take a look at something that makes us think a little bit. So the example I'm going to take it is a nozzle. So that's going to be the easiest thing. And a nozzle, if you thought about it, metal, it's not going to actually move. It's not actually going to deform if it's made out of metal. All right. So bear with me for a second while I get a drawing up there, and then I'll give you a chance to draw it down yourself if you'd like. Okay, so a little less radical numbers than last time. Let's imagine you have this nozzle and you have water coming out, or a fluid coming out at 10 feet per second. Okay, what difference would it make, though, if the nozzle wasn't stationary to how the water looked to us if we were observing? So if we were a stationary observer, I'll just draw in something to try to give a little picture of that. Okay, so that's our eye, and we're a stationary observer, and right there we see the water going out, and we see it going out at 10 feet per second. Okay, what if this nozzle, for example, was like on a truck or something like that, and that was moving? Well, what would we actually see? Hopefully it makes sense to you that if the truck was moving this way, the water would still exit at 10 feet per second relative to the nozzle. Let's say this exit of 10 feet per second is due to some sort of pressure in there. And there's a tank back here, and so the tank is on the truck, and the pressure, the water comes out of that tank. Poor drawing, but hopefully it makes sense to you, and the water comes out at 10 feet per second. Okay. Well, if the tank was moving along, that pressure in the tank would not be changing. And so therefore the change in pressure from the tank out to here would be the same, and we would still get a speed of 10 feet per second relative to the nozzle. Okay, but on the other hand, what would you see? What would you actually see? Well, if the nozzle was moving along, the water would actually look to you to be going faster than 10 feet per second. It would, and it turns out that it's simply additive. It's simply additive. If this whole truck was actually going 10 feet per second, and excuse my writing, I'm writing upside down here. Okay, then to your the water exits 10 feet per second relative to the nozzle. To you, it's going to look like the water's going 20 feet per second relative to the ground. All right, simple enough. I know hopefully you've done a little bit of that in physics, but let's get the terminology that they have, that they end up using in the book. Okay, I'm going to erase that 10 feet per second and give it a symbol. All right, and hey, when I do this work on these little board that I have at home, and sometimes that's really the best I can do, but in the past it seems to work well with students. I'm being really brief in my symbols and my explanations, but it's in the book, and certainly if you have questions, you can write it down. So basically, some symbols that the book uses. W is speed of a fluid relative to a control volume. So in this case, W would be 10 feet per second. Okay, V sub control volume, that's pretty clear. That's how fast the control volume is moving. And then the book uses V for the absolute fluid speed. The absolute fluid speed, say, relative to observer or someone who's stationary. So absolute fluid speed. So what did we do in this case? I ended up making this number 10, and this number was 10. And ended up adding that we got that the absolute fluid speed was 20. Well, it's worth probably writing down the equations the way the book does it. So there are a couple different ways that the book's equation is written in the book. And let me get those down there. Okay, so the book it presents the formula in various forms at various times. This is probably the main one here. Okay, that if you want to get the absolute speed of a fluid relative to some sort of stationary observer or point, and you know the speed of the control volume, and you know the speed of the fluid relative to the control volume, well, you just add them up. And that's what we did earlier. We made this 10 and this 10, and we got a speed of 20. Okay, conversely, sometimes you actually know the absolute speed of the fluid, and you know the speed of the control volume, and you're thinking, what is the speed relative to the control volume? And you can do that difference there. Okay, so let's just go ahead and do just two quick examples where we have that same 10 feet per second, and I'll get that up there and let you think about it for a second. I don't even know if you need to write these down, but I think it's worth thinking about. Sorry, I got a mistake in there. Let me just bear with me for a second. Okay, so trying to take a look at that picture above, what if the nozzle was moving to the left at 5 feet per second? How fast would the water appear to be moving to you? And then part B is, what if the nozzle was moving to the left at 10 feet per second? So I'll let you guys just think about for a second. If you want to pause and write down, freeze the screen and come up with your answers, go for it. All right, so A, if the nozzle was moving to the left, sorry about this pen, at 5 feet per second, okay? Well, then it if the nozzle was stationary, the water would be going 10 feet per second, but now it's essentially being drawn back at the nozzle's being drawn back at 5 feet per second. And what we would actually see is the water coming out at 5 feet per second relative to the ground or relative to some sort of stationary point. And you can see that actually from this equation. W is 10 feet per second relative to the control volume, and the speed of the control volume is -5, and so then we're going to end up getting 5 feet per second. And it's kind of a weird one to think about. What if this fire truck were moving to the left 10 feet per second, and then the water was coming out at 10 feet per second relative to the nozzle? What would you see? Well, hopefully your intuition tells you that the speed of the water is going to be 0 feet per second. And that's actually right. The water, relative to you, the water's just going to come out and it's just going to look stationary. It's not looking forward, not moving forward. So kind of an interesting thing to think about. Okay, good. All right. So that relative velocity idea is pretty powerful, and you can do a lot of good problem solving with it. I want to get back to the rotation and think about what's going on in the rotation, but first I'd like to take an example and see if you can work your way through it. So this is an example for a jet engine. So for a jet engine, maybe a way to think about it is you're looking up at the sky at a jet engine, you see the jet moving along, and then you see that exhaust trail going behind it. And how does the speed of the exhaust trail actually relate to the speed of the jet? So bear with me for a second while I get the problem up there. So I'll just go ahead and start by getting the actual picture. So give me just a second. And I'll give you a part of the picture. Okay, very crude, but that's the jet engine. And what we're going to do is, what the jet engine's going to do is there's going to be an inlet for fuel to come in. So fuel's going to come in there like that. Okay. And 88 feet per second is 60 miles per hour. So this is 600 miles per hour. So this is attached to a wing and it's moving pretty fast at 600 miles per hour. Hey, for large jet engines, sometimes these inlet areas and outlet areas are huge. And for this problem, they're going to be inlet and outlet area is going to be huge. Okay, what's going to happen is that the fuel, as the plane moves this way, there's going to be air that gets taken in through this opening right here like that. And then we'll get an explosion. The fuel will mix with the air and we'll get an explosion, and the exhaust will end up coming out over here like this. So we're going to have exhaust coming out here like this. Okay, and let's see if we can go ahead and work out some numbers. The things I'm going to ask you to do is figure out, hey, what's the mass flow rate of this exhaust? All right, and then secondly, what is the speed of the exhaust? The speed of the exhaust, say, relative to someone down here on the ground who's just watching it go by. Okay, so let me get some numbers up there. Bear with me for just a second. Okay. By the way, what you might want to do is you might want to pull out table C.1 in the book that gives density of air elevations, because this is going to be at some sort of elevated location. We're going to do 5,000 feet. So the jet engine's at 5,000 feet. Its inlet area is huge. Inlet area is 8 feet squared. Outlet area not quite as big, 6 feet squared. Okay, there is fuel coming in, and the fuel flow is a lot of times not that large, and so it's going to be 12 slugs per minute of fuel. Okay, and then an additional thing you need is the outlet density of the exhaust. So the density of the exhaust, something that you'll learn to do in ME 128, is low, 0.0015 slugs per foot cubed. All right. So that's actually everything we know. I believe that's everything we need to know to do this problem. Okay. We got the jet engine going 880 feet per second. We've got 12 slugs per minute of fuel coming in. We've got an inlet area of 8 square feet, and we've got an outlet area of 6 square feet. So this area is the outlet area. This area is the inlet area. Okay, and that's going to be enough for us to start with our first question. What is the mass flow at the outlet? What is the mass flow at the outlet? Okay, so I would encourage you to pause for a second and see if you can start figuring that out. I'll give you one hint. It's continuity. Mass flow in is equal to mass flow out. And we'll start working through the numbers. Good. Okay, so basically what we want to do is we want to figure out the mass that comes in here. Let's say the mass comes in here is, by the way, I'm sorry, I should have said that. We're going to figure out the mass flow at the outlet in slugs per second. We're going to do slugs per second at the outlet. So let's say that this was a mass flow rate in was 10 and this was 12, then we should have 22 coming out if it's steady state. So that's what we need to do. So we need to get the mass flow at the inlet. Okay, so we figure out we can figure out mass flow rates a lot of times by doing density times speed that is perpendicular to the inlet area times the area. So actually at the inlet, this isn't looking that bad. Okay, we know the cross-sectional area. It was given as 8 feet squared. Okay, we know how fast is air actually moving in there. Well, it's going to be, this air out here is stationary, but it essentially is going to enter into this control volume at 880 feet per second. So we've got that. And then we need to get to the density. So, hey, for practice, I encourage you to do this. I did this earlier, and for elevation of 5,000 feet, well, let's look it up really quickly. Let's make sure we got that. So, worth doing. At the end of the book, Appendix C, I believe it is. B is physical properties of fluids. B.3 is properties of the standard atmosphere at different temperatures, but we got to go to table C. So at 5,000 feet, I have a density of air of 0.002048. 0.002048. So I'm going to write that down. 0.002048. A speed of 880, and a cross-sectional area of 8. Okay, so let's take a look at that and see if that works out. This is slugs per foot cubed, this is feet per second, and this is feet squared. So we're going to end up having feet cubed over here and feet cubed in the denominator over there. So we should get a slug per second flow. So let's go ahead and multiply that and see if we can figure that out. Okay, so my calculator is giving me 14.418 slugs per second is entering this surface over here like that. Okay, so the question is, what's the mass flow rate out? Well, that's not that hard to do. If I took and I'll do this below, if I just did a quick drawing, just very crude drawing, you can just see it from the numbers. If in is equal to out. Okay, so here's my control volume, and I need to make a little adjustment. 14.418 in here, 12 here, and then this total in has to be balanced by total out. Hopefully some of you caught the little bit of an error that I was making. This is in slugs per minute, so we should convert that to slugs per second. And so 12 slugs per minute is the same as 0.2 slugs per second. So we've got to get 14.618 coming out. 14.618 slugs per minute. Okay, so that's a good review of continuity, but what does that have to do with what we worked on a few minutes ago? We were working on relative velocity. And so the two questions that I was asking in this problem was, first of all, hey, what is the mass flow rate at this outlet? And then secondly, how fast is it going relative to the ground? So we've got to take this 14.618 slugs per minute, that 14.618 slugs per minute, and convert it into a speed. That's our first thing to do. Think about how do we convert that to a speed? And once again, that's that basic equation. M dot is rho VA, and you have everything you know. So I would encourage you to pause the video, work through and work out a speed. I'll be doing myself. What is the speed of this stuff coming at the outlet using M dot VAC? Hey, you guys, I had a mistake earlier when I wrote on the whiteboard. I wrote 14.6 slugs per minute. That was per second. Sorry about that. Okay, so I'll pause for just a second here. That this basic equation, I want to solve for the speed coming out of the control volume right there. The speed coming out. Not thinking right now whether that's relative speed or absolute speed or whatever. So clearly what I'm going to have to do is do m dot divided by the density and divided by the cross-sectional area. So that's what I did down here. I took the mass flow rate coming out and I divided it by the density, and that density was 0.00518. 0015. You'll learn how to do that in ME 128. And then I was dividing by the cross-sectional area of 6 foot squared. So I'm going to crank through that on my calculator and hopefully I get a pretty large speed. Okay. So I got that it's coming out at I'm sorry about that. I got that it's coming out at 1,624 feet per second right there like that. Okay, so now is the question that was asked though, what is the speed of the exhaust relative to the ground? What is the speed of the exhaust relative to the ground? And maybe before I take a look at that, I should put those basic equation, that basic equation we have up there, and so that we can look at it and think about it a little bit. So I'm going to erase some stuff that was up on the board and get that basic equation that we had up there. So bear with me for just a second. Okay, so thanks for waiting. So there's our basic equation if we have a moving control volume, which is what we have there, is that the absolute speed of the fluid, say relative to the ground or to a stationary absorber, is equal to the speed relative to the control volume plus the speed of the control volume. Okay, well this is 14.6, what kind of speed is this? This is 14.618 slugs per second coming out of the control volume. And so this is how fast the fluid is moving relative to the control volume. So in this equation here, between these three terms, the 1624 is W. The 1624 is W, is speed relative to the control volume. Okay, so we know W, okay? And then we wanted to get speed relative to the ground. So then we have to do a little bit of thinking about positives and negatives. So this stuff is going 1624, but the control volume is going 880 that way. So they're opposite. So basically what we would do is we would put a 1624 here and a negative 880 there to get the speed relative to the ground. So you get 1624 minus 880. Should be able to do that in our head. Okay. And so our answer there is 744 feet per second. So you got this plane going 880 feet per second that way, and then the exhaust is going 744 feet per second the other way. And that may seem a little strange, but again, the plane is really shooting that exhaust out because of that explosion. Okay, so that's some good practice with relative velocity, which is in and of itself is a good topic to get good at. Okay, so what we want to do then is see if we can apply that to understand what's going to happen with these rotating sprinkler, which is a classic example of a case where we use fluids to get something rotating, or rotation is part of the interaction between a fluid and a control volume. So just want to think about what's going on really quickly, and I'll just get this back up here again and try to make sense of it. So this is that device here like this. We're imagining that the water's coming out here like this. And when the water comes this way and makes this turn up, we end up getting rotation like that. So we end up getting the pipe rotating like that. Okay, well right now let's just imagine it's stationary and this water comes out at 10 feet per second. Okay, then as it rotates, the water is going to continue to come out at 10 feet per second relative to the pipe outlet. And that is because basically there's a certain pressure of water coming up, a certain flow this way and a certain flow that way. So the exit speed relative to this pipe has to always be the same. If there's, say, 2 gallons per minute coming here like that, and 1 gallon per minute that way, 1 gallon per minute that way, then we got to have a gallon per minute coming out. Okay, but then what happens to the speed relative actually to this point? Well, as this starts rotating, okay, then the speed relative to this the speed relative to the pivot becomes less. I did not put that very well, so let me try to put that again. Okay, so right now let's say that this is 10 feet per second, and this is our pivot here like this point like this. It's 10 feet per second relative to the pivot, okay? But as this starts rotating and has speed like that, the speed of the water coming out relative to the pivot actually ends up decreasing because of this movement of the actual pipe itself. And that ends up being important because when we work out torque, okay, when we work out a torque on a fluid, again, it is the speed relative to the pivot that we use when we figure out the torque on the control volume. All right, I think it's worth actually jumping in and working on an example. So what we're going to do now is take the same situation where we had 1 slug per second of water. That first example earlier on, we had 1 slug of water coming in to our control volume. So let me try to write it, and I'm gonna make it much less, even less geometry than before, or a little bit less detail than before, and see if we can make sense of it. Okay, so this is an attempt at a isometric or 3D view. Very crude, but let me just get it up there. Okay, so we got this water coming in and it splits where some comes out up over here and some comes out over there, and then this thing is going to start rotating. So basically if I tried to draw the rotation, it would be like that. It would be rotating the opposite direction in the sense that the water goes, so it's rotating. Okay, and then what kind of torque are we actually going to get on the water once it's sped up? All right, well let me get the data up there and we'll take a look at the problem and give you a hint on how to get started. Okay, so we got the sprinkler rotation, and let's say it really gets moving, all right? So like 1 revolution per minute, that would be incredibly slow for a sprinkler. 60 revolutions per minute, that would be 1 revolution per second. Well, if you ever see those things, sometimes they really get going. So we're going to get it going at 285 RPM. Okay. So that's the rotation of the sprinkler, 285 RPM. Okay. Some other, I think, information that we actually would want to work out. Hang on for just a second. Yeah, actually we can just go ahead and get at it because you already have all the information about it. Yeah, just trying to think of how to put it. Okay, so here's our 2 questions that we want to figure out. I want you to figure out how fast the water, we want to figure out how fast the water is going at the exit. So this water that comes out here like that water right there, how fast is it going at the exit? And then we want to figure out the torque of the sprinkler on the water, given that information. Okay, so let me just give you a hint before you get started. The first thing you're going to want to do is you're going to want to take that large number, that 285 RPM, and try to figure out how fast it is that one of the angles where the water exits is going. So basically taking a look at it, we want to figure out how fast this is going. So what I would encourage you to do is draw like a picture of this, like this, of the sprinkler, and then try to take this elbow right here and figure out how fast it's moving. So I'm going to draw that, and I encourage you to draw that yourself and try to get the question up there. Okay, so there's a picture. There's basically sprinkler arm and elbow, sprinkler arm and elbow. And let's just say that the whole thing is turning at 285 RPM. How fast is this point out here going? How do you work that out? Okay, and let me put an equation up there to remind you, and then see if you can, you might want to pause the video and see if you can work your way through it. If we have something rotating with a certain angular speed, okay, we can say its angular speed is equal to the absolute speed of any point divided by how far it is the pivot. Conversely, the speed of any point is equal to the angular speed of the device times the distance from the pivot. So those are two basic equations that we got. So if we're trying to figure out the speed of this point right here, we can figure out the speed by multiplying it, taking the angular speed of this whole device, and that's the 285 RPM, and multiply by the radius. So once again, we can figure out the speed of that point there by taking the angular speed of the device and multiplying it by the radius. All right, note this angular speed needs to be in radians. So you're going to have to take this 285 RPM and convert it into radians. Reminder, the distance was 1 foot. We made the math real easy. So once again, I encourage you to pause, see if you can come up with a speed. We're going to try to come up with a number in feet per second, V in feet per second. I'm going to do a preliminary calculation where I work out the angular speed. Okay, so the angular speed, I got a really large number, but maybe that makes sense. It's 285 revolutions per minute. So divided by 60, I'm getting over 4 revolutions per second. So that would be a revolution is a lot of radians. A revolution is 2 pi radians. So, but anyway, here's the math. I got revolutions per minute, and I want to make it into radians. So there are 2 pi radians per revolution, and then I want to do it per second, so 1 minute per 60 second. So I get almost 30 radians per second. Man, that thing is really, really, really turning. Really, really turning. I'm going to check that number again just to make sure about that. So 285 times 2 times pi, that's 1,790 radians per minute divided by 60. Yep. Okay, so then what I wanted to do, why did I do all that? I wanted to use this equation to figure out how fast that thing is moving. So I wanted to do omega times r. So that's going to be 29.85 radians per second. times 1 foot, and radians is basically a unitless number. So I get the speed is 29.85 feet per second. Okay, and so that is the speed of like the elbow. The elbow is 29.85 feet per second. 29.85 feet per second. Okay, so why did we do all that? Well, the reason we're doing that is we're trying to figure out, hey, what's the torque on the water? And our basic theorem is that if we take a look at control volume, if we can figure out the difference between the angular momentum in and the angular momentum out, then we can work that out. So what I'm going to do is I'm going to take this drawing right here and redraw it and try to get some numbers on it that allow me to work the torque. So I'm not going to show a lot. I'm not going to take the time to actually draw in a control volume that is like a box or a shape of some sort. We're further along and we ought to be able to understand how to do it without working our way through that. Okay. Okay, and bear with me for just a second while I look up a number earlier that we need. Okay, so in short, we've got this water emerging here at 31.3 feet per second. That's what we did earlier. If that 1 slug per second came in, it split with half of it going this way and half of it going that way. And because of the size of this outlet, we noted that the water has to emerge relative to this opening at 31.3 feet per second. So 0.5 slugs per second come out. Okay, so we've got that. Now, we know that this elbow right here, which I could maybe draw in a little bit, that's that elbow where it makes that turn, is moving because of the revolutions per minute at 29.85 feet per second. Okay, we would like for this water that moves here, this water that comes up and then goes here like this and goes like that, we would like to figure out m dot r v theta at the outlet. Okay, where strictly speaking, v theta is the speed perpendicular to this lever arm and also relative to the pivot. Okay, relative to the pivot. So 31.2 is actually relative to that elbow, but that elbow is moving at 29.85. So you can see that relative to this pivot, if I tried to put like a line right over here, that relative to this pivot, this water is actually not moving that fast. So this V right here is going to need to be that 31.3 minus that 29.85. So let's go ahead and do that calculation and figure out what the angular momentum at the outlet is, the angular momentum flow. So I got my m dot was 0.5 slugs per second. Okay. I've got my r, which is 1 foot. And you might want to work out the relative speed yourself. I'm going to try that myself. 31.3 minus 29.85. I haven't been very precise about digits, but it's going to be fine. Okay. So again, I'm trying to get the angular momentum flow out over here, and there's my basic relationship for angular momentum flow. I got 0.5 slugs per second, a radius of 1 foot, and 1.45 feet per second speed relative to the pivot. Okay, relative to the pivot. And then I just go ahead and crank all those things together. Okay. Okay, and I get 0.725. All right. If you think about units, okay, always looking for a pound or always looking for a newton. I've got a slug, foot, a second, and a second. I have a slug foot per second squared, so I'm going to get 0.725 foot-pounds. Okay. Okay. And what actually direction is that? Well, this water is being turned that way. This water is being turned that way. So that is counterclockwise. Sorry about my writing. It's kind of hard to work with there. Counterclockwise. How about this water over here? Okay, how about its m dot RV? Well, its m dot's going to be the same. 0.5 was going this way. Its r was the same, 1 foot. And its relative speed is going to be the same as well. So it's also going to be 0.725. So we have, and it's also going to be counterclockwise. So we have 0.725 counterclockwise coming out of the other one. And we have a total, we can just add those two up, 0.725 plus 0.725. And I get 1.45 foot-pound counterclockwise. Okay. So that torque is 1.45 foot-pound counterclockwise. So if you take a look back to the example that we did at the beginning, we got a much larger torque. So what happened at the beginning was that sprinkler itself was stationary. That was stationary. And we got a really, really large torque, which started accelerating. And then maybe later on when it comes by, it's going faster. And so the water coming out is not going as fast relative to it, so we get less torque. And eventually we settle down to the point where the rotational speed of the sprinkler is such that the relative speed coming out is actually 0, and at that point there is near 0 net torque on the water, and as a consequence there is 0 net torque on the sprinkler, and it just reaches that constant speed. It builds up to a constant speed. Okay, so hopefully you had a chance to crank through those problems that I've been doing and get a little bit, make a little bit of progress on it on your own. What to do from here? The next thing to do is to practice with the homework. So I would encourage you to take a look a little bit through chapter 5, in particular before you try the last problem on homework number 6. The last problem on homework number 6 is the problem with a rotating arm in a dishwasher, which is not an easy problem. So I encourage you to take a look at figure 5.4 and a little bit of work there. And then move on and try that last problem. I am going to provide some hints on homework number 6. So give that your best shot, and then be prepared for lecture number 2, which I'll be posting a little bit later on this week. We're going to move on to chapter 6, and we'll get going on that new material. All right. So as always, feel free to email me with questions. I will be sending you out an email providing guidelines on what we're going to do. Regardless, though, I'm pretty sure we're going to have 2 weeks per lecture, 1 more week lecture this week, and then we got spring break. So that is it, and I'll be chatting with you either by video or by Canvas soon. Take care.